Capillaries are the site for interchange of material between the blood and the tissues. And we know that the capillary is made up of this tube of vascular endothelial cells. Now there is a little bit of exchange between the blood and tissue fluids in the venules, not that much. In the arterioles the walls are too thick. So here we have our vascular endothelial cells, individual nucleated squamous cells. So there we have a capillary. Now the first method of interchange between the blood and the tissue fluid is simply diffusion. Diffusion, you might remember, is the tendency for substances to intermingle until their concentrations become equal throughout. And diffusion will take place down a concentration gradient. So here, if we have a substance at relatively high concentration, that will diffuse down the concentration gradient to areas of lower concentration of that particular substance. So for example, in the capillaries we have the red cells, the erythrocytes, these biconcave discs, and they're darker on the outside because they're thicker on the outside. And of course these are carrying oxygen. And here we have a tissue cell which has been happily using up oxygen. So as these cells use up the oxygen, the concentration of oxygen in these cells goes down. But the concentration here is relatively high. So the simple diffusion of the oxygen first into the tissue fluid, because remember this whole area is surrounded by tissue fluid. All round about the cells we have the tissue fluid, the interstitial fluid surrounding the cells. So the oxygen diffuses first into the interstitial fluid, then into the cell. And in the cell, of course, it can be used by the mitochondria to generate the energy. And in the same way, carbon dioxide is going to build up, because as the cell metabolizes, it's going to increase the amount of carbon dioxide. So the amount of carbon dioxide in the cell is going to build up. But as the blood here has come from the lungs, this is blood in the systemic circulation, it's been through the left side of the heart, then the amount of carbon dioxide here is going to be low, but the amount of carbon dioxide in the cells is going to be high. So now the diffusion gradient is in that direction. It's diffusing from areas of high carbon dioxide concentration, firstly into the interstitial fluid, and then into the blood, where the levels of carbon dioxide are lower. And this is happening all the time. So the cells are constantly using up oxygen. The cells are constantly producing carbon dioxide. But the blood is constantly arriving high in oxygen and low in carbon dioxide. So the dynamic nature of the circulation is why the diffusion gradient is maintained. This, of course, is why you run into problems pretty quickly if you don't have circulation to an area, because the cells won't get the oxygen, they won't get rid of their waste products. Now that's simple diffusion. Now oxygen, carbon dioxide, hormones, glucose, amino acids, waste nitrogen can go in and out of the capillaries by simple diffusion. Now we know that there's these intercellular clefts between the individual cells. So some diffusion will take place through these intercellular clefts. That's going to make it a little bit easier for substances to get in and out. And also in some tissues you might remember that cells have fenestrations. These are holes through the cell. And if there's holes through the cell, these fenestrations, that will also make it easier for substances to diffuse in and out of the blood, between the blood and the interstitial fluid. Now, the path that things take is somewhat determined by the solubility of the substances. So you probably know that there's water-soluble substances and there's fat-soluble substances. So water-soluble substances such as glucose, amino acids, water-soluble hormones could be included in this, such as thyroid stimulating hormone or follicular stimulating hormone or luteinizing hormone. They're water-soluble hormones. They travel in solution in the plasma. Also the water-soluble vitamins, the vitamins B and C, would also fall into this category. The water-soluble substances cannot diffuse through the cell membranes. Now, the reason for this is that the cell membranes that surround the cells, you might remember this, the cell membranes, each cell is surrounded by an individual cell membrane, and these cell membranes are made of phospholipids. So if a water-soluble substance comes up against a fatty membrane, it's not going to be able to diffuse into that membrane. This is very important in pharmacology as well as physiology. So the water-soluble substances, glucose, amino acids, hormones, water-soluble vitamins, can't diffuse directly through the cell. And because they can't diffuse directly through the cell, that means they've got to diffuse through the intercellular clefts, or if a cell has fenestrations, through the fenestrations. Because they're water soluble, they can't get through the fatty cell membrane. But other substances are fat soluble. So oxygen and carbon dioxide are such small molecules, they are fat soluble. So they can actually, when an oxygen molecule comes to the edge here, it can just diffuse through the cell. Likewise, a carbon dioxide molecule can simply diffuse through the cell because they're small and they will dissolve into fatty tissues. Steroid hormones diffuse through the cell membranes directly. So cortisol, estrogen, testosterone, T3 thyroid hormone are fat soluble hormones. They can also diffuse straight through because they're fat soluble. And the fat soluble vitamins. Remember, A, D, E and K are the fat soluble vitamins. They can just diffuse straight through as well, whereas the water soluble ones have to go through the gaps or fenestrations. In the sinusoids, the intercellular clefts and the fenestrations are much larger, so proteins and red cells can get in and out. But generally, the gaps in the capillary are too small for proteins to be able to get out in the continuous systemic type of capillaries. But more of that on proteins later on. So that's the first mechanism, simple diffusion. The second is transcytosis. Trans means across. The Trans-Siberian Railway, where does that go? Cross Siberia. Trans means across. Cytosis, of course, is a suffix meaning to do with cells. So transpsychosis means across the cells. And this is a special process called pinocytosis. Now what happens here is, imagine this is the, let's do a blow-up version of one of these. Imagine we have the surface of the cell here. So here's the surface of the cell. Now, what can happen is if there's, for example, large lipid molecules or insoluble molecules, a lot of insulin is actually taken into the cell via this mechanism. Although insulin is water soluble, it can diffuse as well. But larger molecules that need to go through the cell. So what happens is the larger molecules arrive on one side of the cell membrane. Doesn't matter which it is. This can be from the blood to the tissue fluids, or it can be from the tissue fluid into the blood. And what happens is the cell forms a little indentation like this in the membrane, and the material is kind of swallowed up, as it were, by the cell. This is called a pinocytic vesicle. Now, a vesicle is a fluid-filled space in the cell. Pinocytosis, pino actually means to do with drinking. So pinocytosis literally means cell drinking. So then what we end up with is this vesicle containing the molecules that want to be transported, and now inside the cell, like this. And they will simply just move across the cell like this. It will move to the other side. And then once at the other side, you'll get the reverse process here, where the vesicle will merge with the other membrane, allowing the material to get out. So this process where it's taken in on this side, this is called endocytosis. Taking into the cell, endo means in, endocytosis. And this one, it comes out, is called exocytosis. Exo, of course, as in exit. So the pinocytic vesicle is formed via endocytosis. It moves across the cell, and it goes on to the other side by exocytosis. So we've mentioned insulin, we've mentioned large lipid insoluble molecules. You see, if there's lipid soluble molecules here, the lipid soluble molecules can actually just diffuse through the phospholipid cell membrane on both sides. The phospholipid cell membrane around about the cell is not acting as a barrier because the lipid soluble material can diffuse into that. But the lipid insoluble material, the things that won't dissolve into lipids, can't get through that way, so that's when the pinocytosis is used. It's not used a lot. Think of another example. Antibodies and some proteins, for example, go from the maternal into the fetal circulation via this process. So this could be an antibody in the mum's circulation, an immunoglobulin to protect against infection, and we want that to go from the maternal circulation into the fetal circulation. And that's important because if the baby is not born with her maternal antibodies, they don't have the passive immunity, and babies would probably all die with infection within a few days of being born if it wasn't for this process, because babies have to be born with mother's antibodies. They might only stay in the circulation for a few months, but that gives baby time to make their own active immunity. So I think it's fair to say without this process, taking antibodies from the maternal to the fetal circulation, none of us would be here. So large lipid insoluble molecules and antibodies in some proteins. So that was the first process, was diffusion. The second was transcytosis. The third is called bulk flow. Now, bulk flow is necessary to control the movement of ions, different molecules, particles in a fluid. And this is what regulates the relative volumes of fluid in the intravascular compartment in the blood and in the interstitial compartment between the cells. So we need this regulation of material. We need the regulation of the concentration of proteins and the regulation of the amounts of water. We don't want the blood to become fluid overloaded and the interstitial fluid to become dehydrated. We need this balance. And this is facilitated by bulk flow. And there's two processes here. There's filtration and there's reabsorption. These are the processes. And these are controlled, facilitated by two factors. One is two main factors. Hydrostatic pressures and osmotic pressures. So for example, at the arterial end of the capillary, when blood's coming in, the hydrostatic pressure in the capillary is going to be relatively high, and that's going to tend to force water out into the interstitial spaces, giving rise to the formation of the interstitial fluid. But we don't want the fluid, don't want the tissues to become too soggy. That would be edema, wouldn't it? So what you also have in the blood are the large plasma proteins. These will exert an osmotic effect. And then when the hydrostatic pressure, when the blood pressure is lower at the venous end of the capillary, because the blood's going to exit. Blood's going to exit via the venous end of the capillary. So this is the arterial end of the capillary with the blood going in, flowing through, exiting via the venous end of the capillary. Here, the osmotic pressure is going to be greater than the hydrostatic pressure, so fluid's going to get sucked back in. So it's the balance between the hydrostatic and the osmotic. But I'm going to give you figures on this in the next clip, because we do need to do that in a bit more detail, because it's a very important process. But what I think you can see it means is that tissue fluid is going to be formed at the arterial end, flow over the cells, keep the tissue fluid nice and fresh, be reabsorbed. So we have another aspect of circulation. So all this circulation through the capillary is microcirculation. There's microcirculation of the blood, but also of the tissue fluid. Because it's going to be formed, flow over the cells and reabsorbed. So the microcirculation facilitated by the arrival of blood in the arteriole, the exiting of blood via the venule. And it's these three processes, the diffusion, the transcytosis and the bulk flow, that maintain the viability of all body cells. They all depend on this vital physiology of the capillary, which is often overlooked in a lot of texts and courses, but it's absolutely vital to maintain the integrity of our tissues, maintaining the integrity of these cells, allowing the cells to maintain the integrity of the tissues, and the tissues, the organs, and the whole functioning of the body. Because life actually operates at the cellular level. It's the viability of the individual living cells. These cells that possess this amazing phenomena called life, all acting together to generate our lives.